Hi guys, how's it going? I hope everyone's well, and I hope you're keen to do some physics. Tonight I'll be doing questions 29 and 30 of the 2017 HSC Physics paper. Okay, question 29 asks, a spring is used to construct a device to launch a projectile. The force F required to compress the spring is measured as a function of the displacement x by which the spring is compressed. So here we have a compressed spring, and that launches a projectile. We have its uncompressed length and its compressed length. Pretty sure people know how springs work. The potential energy stored in the compressed spring can be calculated from the formula EP is equal to half kx squared. So that EP means potential energy, in this case elastic potential energy, where k is the gradient of the force displacement graph shown. So that's just the information for question 29. Question 29a asks, a projectile of mass 0.04 kilos is launched using this device with the spring compressed by 0.08 meters. Calculate the launch velocity. This is a 4-mark question, and there is a fair bit to it. The first thing I'll say is that in order to calculate the launch velocity, is that we have to assume that all of the potential energy in the spring gets converted into the kinetic energy of the projectile. So that's what we need to know. The first formula I'll bring up is the equation for the potential energy of the spring, which equals half kx squared, where x equals 0.08 meters as given above. Now k is the gradient of this diagram. To calculate the gradient, so frequently gradient is given by letter m, which equals rise over run. And if you've studied a bit of mathematics, you might remember this as y2 minus y1 over x2 minus x1, which just refers to the coordinates of 2 points on your line. So imagine, so this is a pretty straight looking line. Imagine I can draw a pretty straight line like this through all these points. If I could draw a straight line, that's okay anyway. Now I can take 2 points here. I'm going to take these 2 points. I'm going to take the 2 points at the furthest point on that line, or from the furthest point on that line. Now it looks like I can say that y2 is going to be 24. So I'm going to call this point 2. I'm going to call this 0.1. So, well, this is 0.1. And it doesn't matter what I call 2, what I call 1, as long as I'm consistent. So, looks like y2 has a value of 24. So this equals 24 minus 3 divided by values x2 and x1. So the x coordinate of 0.2 is 0.08. And the y coordinate, the x coordinate of 0.1 is 0.01. So that equals 24 minus 3, which is 21, divided by 0.07, which equals 300. So we can say that k, which is the gradient of this line, which we just found, equals 300. And it's 300 newtons per meter, because the units of the rise in this case were newtons, and the units of the run, which is the horizontal axis, were in meters. So k now has units of newtons per meter. Cool. So if I go back to this side, and I'm saying my formula for the potential energy of the spring is half kx squared, I've now got k is equal to 300 newtons per meter. And I can actually calculate that. And if all of my potential energy is converted into kinetic, I can now calculate my kinetic energy. And we'll see why that's so important pretty soon. So, if I plug that into my formula, I see that EP is equal to half times 300 newtons per meter times 0.08 meters squared, which if I plug that into my calculator equals 0.96 Newton meters, which is actually equivalent to joules. So we've now got our energy as 0.96 joules. So that's good. We want our energy is always measured in joules, or some other type of energy unit, but we just want to make sure we've got energy units there. So that's good. Because we've assumed that all of our potential energy is converted into kinetic, we can now say that EK is equal to 0.96 joules. Now, if we recall our formula for the kinetic energy, we say that EK is equal to half mv squared. This is where our mass is going to be important. So this question is asking us, find the launch velocity. So we need to rearrange this equation for velocity. The first thing I'll do is I'll multiply both sides by 2 to get rid of that half. So I get mv squared, mv squared, it's probably a bit too big, equals 2ek. And then I want to get the v squared on its own, so I divide both sides by m. So I get v squared equals 2ek over m. And finally, I just need v on its own rather than v squared. So I take the square root of both sides. So I get v is equal to the square root of 2ek over m. And that looks like the square root of, once I plug in my values, 2 times 0.96 joules over a mass of 0.04 kilos. I plug that all into my calculator and I get V is equal to 6.93 meters per second. So I had to use two equations there, my EP equation and my EK equation, to find the velocity. And I also had to assume that all of my potential energy is converted into kinetic. That's why that is a 4-mark question. So I think that tallies up with a 4-mark question. There's a reasonable amount of work and it wasn't too easy. So that's pretty good. Okay. Question B. Calculate the range of a projectile launched by this device from ground level at an angle of 60 degrees to the horizontal with a velocity of 10 meters per second. Okay, so if we have a situation, so when we start a projectile motion question, should always draw a diagram, and that looks, in that case, something like this. So we have our velocity, and it gets ejected by, and it lands somewhere over here. Our initial velocity is 10 meters per second, and our angle to the horizontal is 60 degrees. That's good. So we need to calculate the range of the projectile. So we need to know this value. I missed delta x. Okay. So the equation for delta x is delta x equals ux times t. We can find ux pretty easily just by setting up our triangle where we've got u, we've got our angle, we know 60 degrees, so we've got ux and we've got uy, so we know that, that cos of 60 degrees, remember that's our adjacent over the opposite, which in this case is ux, adjacent over the hypotenuse, cos 60 degrees equals ux over u, and remember just ux equals, or u, equals 10, so I'll just rub that out, so I'll just replace that with a 10, so cos 60 degrees equals ux divided by 10, I need to find ux on its own, so I multiply both sides by 10, and I get, so that cancels out with that one, and I get ux equals 10 cos 60 degrees. And through a similar logic, uy equals 10 sine 60 degrees. Now, 10 cos 60 degrees just equals 5 meters per second in this case. 5 meters per second, because that's our velocity, so it's in meters per second. And this is 8.66 meters per second. Cool. So we now get our ux and our uy. Now, unfortunately, there's no way to determine, at the moment, we haven't got any time information. So we have to work that out. Now, delta x equals uxt is really our only horizontal equation for range. So that means in the horizontal direction, we don't have any more information that will allow us to figure out the time. So that means we have to look at the vertical direction to find out the time. To do that, I'm going to look at the equation v equals u plus at. At the moment, I haven't assigned any direction to it. That's just one of my equations that I can use. So v equals u plus at. I know that's the equation I want to use. I'm going to put it in the vertical direction. So I'm going to put my little y's there. So I'm going to rewrite this as vy equals uy plus ayt. Now, people are hopefully aware that the easiest way to do this type of question is that we need something to equal 0 here, because we need to reduce our number of unknowns. We know uy, it's over here, so we found this one. But we want to find the time, because that time will allow us to figure out the time in this question, or in this delta x equals uxt. So, what I'm going to do is I'm going to set, even though I haven't drawn this very nicely, this point here at the apex of the curve, or of that parabola, is the point where Vy, the vertical velocity, the final vertical velocity, is equal to 0. And that's because this projectile has been launching up in a decreasing rate. So it originally was going up quite fast, started going up smaller and smaller, until eventually it stops going up at all, and in fact eventually starts speeding up, going down. So at this point in the middle of the curve, even though it's not quite the middle of the curve in my drawing, but it should be, just pretend it is. At this value, in the middle of the curve, the vertical velocity is 0. My initial vertical velocity is just what we've calculated as 8.66. My final is 0, and t is what I need to work out. So if I sub that onto my equation, I get 0 equals 8.66, times, plus negative 9.8 t. Now if I put that on the other side of the equation, I get 9.8 t equals 8.66. And if I plug that in my calculator, what do I get? I get t equals 0.88. And that approximately gives me t. So that gives me t to the halfway point. Now, in this equation, delta x equals uxt, this is the range at any time t. However, I want to know the range. I want to know the full range of this projectile. I want to know the range for the full time of that path, which means that I need to know the full time. At this point here, I've calculated the time for half. I've calculated half the time. So if I need to know the full time, and I found the time at t half, I can say t half equals 0.88 seconds, and that t full, so I'm just going to say t full equals, that rounds up to around 1.8 seconds, because I only need it to one decimal place. Cool. So now I've got t full equals 1.8 seconds, and if I sub that into my original equation for range, I get delta x equals 5 meters per second, which is my ux, times 1.8 seconds, which gives 8.8 meters. Cool. So we just worked out the range of this projectile is 8.8 meters. And that's a pretty standard projectile motion question, which you'll find in most HSC papers, I think, or at least practice ones. So that was question 29. Let's have a look at question 30. Okay, so it's a 4-mark question. In a thought experiment, a proton is traveling at a constant velocity in a vacuum with no field present. An electric field and a magnetic field are then turned on at the same time. The fields are uniform in magnitude and direction and can be considered to extend infinitely. The velocity of the velocity of the proton at the instant the fields were turned on is perpendicular to the fields. So analyze the motion of the proton after the fields have been turned on. It's a 4-mark question. We're going to need to do some thinking about this one. Probably going to be around 2 marks for the motion of the proton in each field. Now, if we just look at the magnetic field first and pretend the electric field isn't there, when we have a charged particle in a perpendicular magnetic field, and it's always going to be perpendicular, we usually end up with circular motion. And if you can imagine what this is going to look like, if we just look at the motion from the magnetic field on its own for now. So what that looks like is, using our right hand rule, if we set it up so that our fingers on our right hand are pointing to the left, our thumb is pointing upwards, and our palm is should be pointing up towards us. It's towards my face in this case, which means the first force on the particle is actually directly out of the page. It's perfectly out of the page. Now, that's going to result in a motion that kind of looks like this, but imagine that's not actually diagonal. That arrow is sticking out of the page. The arrow is sticking up because the proton's already moving up, but now it's starting to tilt out of the page, and so that's its new velocity. As a result, that causes a new force on that proton, which changes the direction, which pushes it down a bit more, and this is how we form circular motion. So it's forming circular motion. It's not actually going diagonally, but what it is doing is that proton is coming more and more out of the page until it's heading perfectly downwards, perfectly down the page, and then curls back into the page slowly and starts to head up again. So you can imagine that it's actually forming a circle because of the magnetic field on its own. And if you look from the right, it looks like an anti-clockwise loop. So from the magnetic field, it is forming a loop when viewed from the right. So that's what I'm going to write. So the motion of the proton after the fields have been turned on. So the proton moves in a circular path from the magnetic field. Okay. Now we look at what is the motion of the proton due to the electric field. So the direction of an electric field is given as the direction a positively charged particle would travel if it was in that field. Hopefully we all know that a proton is a positively charged particle. So the proton is just going to follow the direction of that field, and it's going to move directly left. So because of the proton, because of the electric field, it's just going to move to the left. And it's not only going to move to the left, it's going to accelerate to the left. Because we have an electric field where the force is constantly being applied, when there's a force, there is always an acceleration. So if a force is continuously being applied, there's a continuous acceleration. So now we've got two motions. We've got a motion to the left, and we've got a motion that is an anti-clockwise circle when viewed from the right. So this is going to form a weird sort of spiral shape that's sometimes called a helix. And it's going to form a helix that is actually expanding as it moves to the left. That's kind of hard to draw. I'm not a very good artist, guys. I'll confess that. So, first thing I'll start just by writing it. So the proton moves in a circular path from the magnetic field. So this circular path then gets stretched out to the left increasing the length of the spiral as it moves further away from its starting point. Now, this is not an ideal, probably not an ideal explanation. It's okay, probably get you the marks, but I'm sure there's better ways to describe it if you want to do that. Now, with a question like this, diagrams are always good. Having this up here is probably pretty good, but I'm going to try and draw the whole thing. So first of all, I'll have magnetic field. I'm going to separate. So if you didn't want to write this as an answer, if you didn't want to put this answer in words, you could separate it into a bunch of diagrams. So if you have magnetic field, you could say viewed from right. We could say we have an anti-clockwise circle of constant radius. So this radius, well, actually I could talk about the radius in a second. So first of all, that's the motion due to the magnetic field. From the electric field, we have a movement to the left. Electric field. So it's just now we've got this proton, and it just moves to the left. But notice, because it's actually moving up and down and up and down the page, I should say, if we looked at it perfectly square on, it might form a shape. It should form a shape that's kind of like this. So it's coming up, and it's coming down, and it's coming up, and it's coming down. And we notice it's actually getting stretched out the more it goes to the left. And that's because it's accelerating in that direction. So that's a 2D representation of the combination of the electric field and the magnetic field, if we looked at it perfectly side on. Now, if you wanted to include the spirals in there, you could also do that, and it's going to look something like this. I'm sure someone out there watching this video can draw this better than I can. I'm not a good artist, and I do not pretend to be, but I do pretend to be good at physics. That's definitely true. So it's going to look something like this, where we've got increasing spirals as we go further to the left. And those are mostly getting bigger, so that's probably good. So if you wrote something like that, and if you drew some combination of those diagrams even better, I think that's going to get you the 4 marks. Oh, and one more thing is we can talk about the radius of this orbit, of this spiral. Now, if we assume that the fields are turned on, but they're not supplied by a constant energy source, or say especially when it comes to the magnetic field, if we assume that they're not supplied by a constant energy source, then we can say that because we have the proton, which is traveling in an anti-clockwise loop, and it's accelerating, it's releasing electromagnetic radiation. And because it's releasing radiation, it's releasing energy, and it should be slowing down, and the radius of that loop, of that spiral, should be getting smaller. So we can say that. That's if the field is temporary. If the field is permanently on, if that field is permanently on, it provides a constant source of energy to that proton, even though the proton's accelerating and releasing energy, the radius will not change. The radius will not change because it's being maintained at its normal rate, or it's being maintained at its level of potential energy. So we can add a little thing here saying, just making sure, moves from its starting point. This forms a spiral path, a spiral of constant radius in a permanent field, permanent electromagnetic field. So, okay. So guys, that was question 30. I hope you enjoyed this. I'm about to sneeze. No, who knows? It's there. Thoughts to come out. Anyway, if you liked this video, please give it a thumbs up. If you disliked it, give it a thumbs down. If you did dislike it, please leave a comment in the comment section below and let me know what I could do better to improve these videos. Okay guys, have a good night.